All right, welcome to The Explainer. I am super thrilled you're tuning in today because we're going to completely flip the script on how you look at the machines buzzing around you. We're unpacking the sensory logic of robotic vision. And honestly, I promise you, the hidden reality of how machines actually perceive our world, it's infinitely more fascinating than any sci-fi movie. We're going to strip away all that movie magic and just look at the raw, beautiful, structured logic of robotic perception. Okay, so let's just dive right into this. It's a highly relatable question, right? I mean, how does a basic little vacuum robot just cruising around your living room actually know to stop right at the edge of the stairs instead of taking a nosedive? It doesn't have a brain. It definitely doesn't feel fear. What it actually has is a highly specific system of perception. And that perfectly sets the stage for our core concept today. But first off, we really have to shatter a pretty massive misconception here. When we talk about robotic vision, we are absolutely not talking about seeing the world the way you and I do. Not even close. Instead, robotic vision is strictly this process of gathering and interpreting raw electronic data. And actually, more importantly, it's a constant, never-ending battle against interference. Engineers call this noise. So your robot isn't, admiring the intricate pattern on your rug. It's literally just crunching numbers, filtering out completely irrelevant signals, all just to figure out what's solid ground and what's empty space. Just a quick look at our roadmap for today. We're covering 6 main areas: how robots actually see, active versus passive sensors, proximity and mapping, wiring and coding action, high-speed event cameras, and finally, designing for the unknown. All right, let's jump straight into Section 1, how robots actually see and process electronic data. We really need to break down this foundational illusion right off the bat. Assigning human traits to machines is just, it's something we all do totally naturally, but doing that completely obscures the incredible reality of how they actually operate. The big myth here is that robots use eyes like humans do. The reality? They process streams of electronic data. When we project our own human experiences onto a machine, we're really missing out on understanding the highly specialized sensory tech that actually lets these systems navigate safely. It's so much cooler than just having eyes. Let's move along to Section 2 and see how this builds into gathering sensory data with active versus passive sensors. So this brings us to the fundamental logic of how sensory data is actually gathered in the first place. You can break this down into 2 main categories. First up, we've got active sensors. These guys emit their own signals out into the environment. Think of it like a bat using echolocation, right? It sends out a high-pitched sound and then just waits for that echo to bounce back. Now, on the flip side, we have passive sensors. These don't send anything out at all. They just sit back and receive existing signals from the environment around them. It's a lot like a human just standing quietly in a room, listening for footsteps. Understanding that specific difference is absolutely key to grasping how a robot interacts with its world. Which brings us to Section 3, proximity, distance, and mapping. Basically, the robotic toolkit. Now, what's really interesting here is this sort of big 3 toolkit we have. Each sensor solves a highly specific problem. Take a look at the ultrasonic sensor. Its absolute superpower is measuring distance, so it's perfect for finding gaps and avoiding collisions. Then you've got the infrared, or IR sensor. Its core concept is proximity, which makes it ideal for sensing stark contrast, like following a black line on a bright white floor. And finally, LiDAR. Oh man, this is your mapping powerhouse. It's used for building those really intricate 3D room layouts. By combining these different tools together, engineers can give a robot a really comprehensive understanding of the physical space around it. Moving right into Section 4, wiring and coding action. How we actually create robot logic. So we've talked a lot about the hardware, right? But how does all that raw sensory data actually turn into a physical mechanical action? Well, this is the literal process of building robot logic. First off, you physically wire a component, let's say an ultrasonic ping sensor, right into the robot's circuit board. But, hardware is completely useless without software. So step 2 is writing the code. For example, you might program a stop if close command that triggers a mechanical response based on that incoming proximity data. And then finally, step 3, you actually have to adjust that code for different environmental surfaces. Because think about it, sound waves are going to bounce way differently off a hard hardwood floor compared to a thick, fluffy carpet. The real magic happens when the wiring and the coding are working in absolute perfect harmony. Let's jump to Section 5, high-speed event cameras and high-speed tracking. Now, let's kick things up a notch and elevate this discussion from basic robotics to some truly cutting-edge science. See, traditional sensors are fantastic for steady, predictable navigation, but they have some major limitations when things start moving too fast. Enter the brilliant research by Davide Scaramuza on event cameras. These advanced cameras completely solve the problem of tracking high-speed motion that traditional sensors just straight up miss. Instead of capturing standard frames like your typical movie camera does, event cameras only record the changes in lighting at individual pixels. This lets robots process lightning-fast movements in real time without getting bogged down by a whole bunch of useless background data. It's a massive game changer.
And finally, Section 6, Designing for the Unknown and Applying this Sensory Logic.
All right, I want to challenge you a bit here to apply the technical logic we've just uncovered. Let's do a really quick thought experiment. Just pause and think about this for a second. If a robot is made completely out of clear glass, could another robot equipped with an ultrasonic sensor actually see it? Keep in mind what we just learned about active versus passive sensors. And this brilliantly illustrates exactly why understanding the underlying technology matters so much. Yes, the sensor would absolutely see the glass robot. Why? Because an ultrasonic sensor doesn't rely on light or human-like vision at all. It uses active sound waves. So even though that glass is completely invisible to the human eye, it is entirely solid. Those sound waves hit the glass and bounce right back, feeding completely accurate distance data straight to the robot's processor. It's just a perfect example of how electronic perception completely bypasses our own human visual limitations. The real-world applications for the sensory logic scale from the super simple to the extraordinarily complex. For a guided practice in a robotics class, you might just choose an IR sensor for a little robot whose only job is to follow a black line on a white floor. Simple enough. But in mission-critical scenarios, like, say, designing a Mars rover, engineers have to select an incredibly robust array of sensors. They need a system capable of navigating completely unknown, dusty, and downright hostile terrain where interference and that electronic noise are just constant everyday threats. But here's the kicker. The foundational logic remains exactly the same. So the crucial takeaway here is that by finally letting go of our own human biases, we can build machines capable of perceiving the universe in ways we can scarcely even imagine. I want to leave you with a final reflection based on everything we've covered. If you were designing a robot from scratch, what completely new sense would you give it that humans simply don't have? A sensor for radiation? Maybe a magnetic field detector? The possibilities for machine perception are quite literally infinite. Thank you so much for joining me for this explainer, and definitely keep questioning how the world around you actually works.